everyone, my name is Elsadday Panjaitan. I'm major environmental engineering from President University. Here, I want to present the application of green chemistry in pharmaceutical industry. Definition of green chemistry. Green chemistry or green chemistry is a field of chemistry that focuses on preventing pollution. In the early 1990, green chemistry became known globally after the Environmental Protection Agency (EPA) issued the Pollution Prevention Act, which is a national policy to prevent or reduce pollution. Green chemistry is an approach to overcome environmental problems, but in terms of the chemical product, the process or the reactions that use. This concept emphasizes methods based on reducing the use and manufacture of hazardous chemical food in terms of design and process. The chemical hazards referred to in the green chemistry concept include various threats to human health and the environment, including toxicity, physical hazard, global climate change, and the depletion of natural resources. Green chemistry concept. Green chemistry is aimed at the impact of industrial product and process on the environment. The main principle in green chemistry is prevention is better than cure. So the goal of green chemistry is to prevent pollution rather than dealing with waste that occurs. The alternative definition of green chemistry that is preferred by the industry is sustainable technology. Sustainable technology aims to meet the needs of the patient without compromising the ability of future generations to meet their needs. Sustainable technology is the main goal of the green chemistry concept. 12 principles of green chemistry. The first one, waste prevention. It is better to prevent waste than to treat or clean up waste after it has been created. 2. Designing safer chemical. Designing safer chemical products should be designing to affect their desired function while minimizing their toxicity. 3. Less hazardous chemical synthesis. Wherever practicable, synthetic methods should be designed to use and generate substances that possess little or no toxicity to human health and the environment. 4. Safer solvent. The use of auxiliary substances should be made unnecessary wherever possible and innocuous when used. 5. Minimize risk of accident. Substance and the form of a substance used in chemical process should be chosen to minimize the potential for chemical accident, including release, explosion, and fires. 6. Real-time analysis for pollutant prevention. Analytical methodology need to be further developed to allow for real-time in-process monitoring and control prior to the formation of hazardous substances. 7. Atom economy. Synthetic methods should be designed to maximize the incorporation of all material used in the process into the final product. 8. Reduce derivative, unnecessary derivation, the protection, temporary modification of physical chemical process should be minimized or avoided if possible because such steps require additional reagent and can generate waste. 9. Design degradation. Chemical products should be designed so that at the end of their function, they break down into inertious degradation product and do not persist in the environment. 10. Renewable feedstock. A raw material of feedstock should be renewable rather than depleting whenever technically and economically practicable. 11. Energy efficiency. Energy requirement of chemical process should be recognized for the environmental and economic impact and should be minimized if possible. Synthetic methods should be conducted at ambient temperature and pressure. 12. Catalysts. Catalyst reagents are superior to stoichiometric reagents. The application of the 12 principles of green chemistry has not yet been fully carried out by chemists, especially those in the field of synthesis, in terms of reaction design and method used to prevent environmental pollution to a minimum. The main focus of green chemistry: A. Alternative route of synthesis process based on anthropic efficiency can be achieved by the use of catalysts and biocatalysts, natural synthesis process. B. Alternative reaction condition based on the use of solvents that have little impact on the environment, increase selectivity, and reduce the amount of waste and emission product. C. Design, use, and production of relative non-toxic chemicals that reduce the potential for accident. D. Use of basic material and reagent that can relieve dependency of fuel oil. E. Evaluation of hazard posed by chemical process, chemical product, and reagent and byproduct. What is the role of green chemistry in the pharmaceutical industry? Pharmaceutical company can influence and improve environmental performance by utilizing green chemistry. Green chemistry is being used to develop revolutionary drug delivery methods that are more effective and less toxic and could benefit millions of patients, some of whom are described here. Post-hormidal-based solid-phase synthesis of antisense oligonucleotides has been modified to accommodate green chemistry principle by eliminating the use and generation of toxic material and enabling the use of valuable material such as amide support and Selding group, thereby increasing atomic economy and cost efficiency. Four types of contaminant found in the pharmaceutical industry. The first one, physical contaminant. Physical contaminant are anything that can be seen with the eye and are not part of the product or raw material. Example of physical contaminant include non-fiable airborne contaminant and foreign material, for instance from production such as metal clip, glass, particles shard of glass, fiber, fragment, and others. The way to minimize this physical contaminant is to clean the tools and rooms every day according the SOP or with a cleaning method that is proven reliable and stated in the SOP. Cleaning this physical contaminant is relatively easy because they are visible and can be directly done with a cleaning tool. 2. Chemical contaminant. Chemical contaminants are unwanted chemical substances and can make a drug product unsuitable. Examples of chemical contaminants include drug active ingredient, intermediate, excipient, chemical reagent, and different cleaning agents that may be left behind during drug production. For example, They are remaining active raw material for product in the machine, even though the machine is still producing drug B. The cleaning method for chemical contaminant is almost the same as for physical contaminant. Often a cleaning agent is needed. Remove impurities. Use cleaning agent that comply with the cleanest class tool require and is non-descriptive. 3. Viable microbial contaminant. Viable contaminant or microbe are infectious material that can be affect drug quality. Example of microbial contaminant are bacteria, fungi, mold, virus, prion, protozoa, and the toxic substances they second. 4. Non-viable contaminant. Example of non-viable source of contaminant can come from paper, equipment, pipe, dust, disinfectant that in a clean room as much as possible minimize the tools or goods that have nothing to do with the production process. Use of green chemistry in the pharmaceutical industry. The first one, glycerol. 2. Aspirin. 3. Atorvastatin. 4. Ibuprofen. To complete what we talk about this topic, let's watch this video.
Welcome to my channel Chem World. Basics of green chemistry. In this video we are going to learn definition of green chemistry, how green chemistry differs from cleaning up pollution, green chemistry's 12 principles, green chemistry's roots in the Pollution Prevention Act of 1990, definition of green chemistry. Green chemistry is the design of chemical products and processes that reduce or eliminate the use or generation of hazardous substances. Green chemistry applies across the life cycle of a chemical product, including its design, manufacture, use, and ultimate disposal. Green chemistry is also known as sustainable chemistry. Green chemistry prevents pollution at the molecular level, is a philosophy that applies to all areas of chemistry, not a single discipline of chemistry, applies innovative scientific solutions to real-world environmental problems, results in source reduction because it prevents the generation of pollution, reduces the negative impacts of chemical products and processes on human health and the environment, lessens and sometimes eliminates hazard from existing products and processes, designs chemical products and processes to reduce their intrinsic hazards. How green chemistry differs from cleaning up pollution. Green chemistry reduces pollution at its source by minimizing or eliminating the hazards of chemical feedstocks, reagents, solvents, and products. This is unlike cleaning up pollution, also called remediation, which involves treating waste streams, end of the pipe treatment, or cleanup of environmental spills and other releases. Remediation may include separating hazardous chemicals from other materials, then treating them so they are no longer hazardous or concentrating them for safe disposal. Most remediation activities do not involve green chemistry. Remediation removes hazardous materials from the environment. On the other hand, green chemistry keeps the hazardous materials out of the environment in the first place. If a technology reduces or eliminates the hazardous chemicals used to clean up environmental contaminants, this technology would qualify as a green chemistry technology. One example is replacing a hazardous sorbent chemical used to capture mercury from the air for safe disposal with an effective but non-hazardous sorbent. Using the non-hazardous sorbent means that the hazardous sorbent is never manufactured, and so the remediation technology meets the definition of green chemistry. Green chemistry's 12 principles. These principles demonstrate the breadth of the concept of green chemistry. 1. Prevent waste. Design chemical syntheses to prevent waste. Leave no waste to treat or clean up. 2. Maximize atom economy. Design syntheses so that the final product contains the maximum proportion of the starting materials. Waste few or no atoms. 3. Design less hazardous chemical syntheses. Design syntheses to use and generate substances with little or no toxicity to either humans or the environment. 4. Design safer chemicals and products. Design chemical products that are fully effective yet have little or no toxicity. 5. Use safer solvents and reaction conditions. Avoid using solvents, separation agents, or other auxiliary chemicals. If you must use these chemicals, use safer ones. 6. Increase energy efficiency. Run chemical reactions at room temperature and pressure whenever possible. 7. Use renewable feedstocks. Use starting materials, also known as feedstocks, that are renewable rather than depletable. The source of renewable feedstocks is often agricultural products or the wastes of other processes. The source of depletable feedstocks is often fossil fuels, petroleum, natural gas, or coal, or mining operations. 8. Avoid chemical derivatives. Avoid using blocking or protecting groups or any temporary modifications if possible. Derivatives use additional reagents and generate waste. 9. Use catalysts, not stoichiometric reagents. Minimize waste by using catalytic reactions. Catalysts are effective in small amounts and can carry out a single reaction many times. They are preferable to stoichiometric reagents, which are used in excess and carry out a reaction only once. 10. Design chemicals and products to degrade after use. Design chemical products to break down to innocuous substances after use so that they do not accumulate in the environment. 11. Analyze in real time to prevent pollution. Include in process, real-time monitoring and control during syntheses to minimize or eliminate the formation of byproducts. 12. Minimize the potential for accidents. Design chemicals and their physical forms, solid, liquid, or gas, to minimize the potential for chemical accidents including explosions, fires, and releases to the environment. Green chemistry's roots in the Pollution Prevention Act of 1990 to stop creating pollution in the first place became America's official policy in 1990 with the Federal Pollution Prevention Act. The law defines source reduction as any practice that reduces the amount of any hazardous substance, pollutant, or contaminant entering any waste stream or otherwise released into the environment, including fugitive emissions, prior to recycling, treatment, or disposal. Reduces the hazards to public health and the environment associated with the release of such substances, pollutants, or contaminants. The term source reduction includes modifications to equipment or technology, modifications to process or procedures, modifications, reformulation or redesign of products, substitution of raw materials, improvements in housekeeping, maintenance, training, or inventory control. Section 2 of the Pollution Prevention Act establishes a pollution prevention hierarchy, saying, "The Congress hereby declares it to be the national policy of the United States that pollution should be prevented or reduced at the source whenever feasible. Pollution that cannot be prevented should be recycled in an environmentally safe manner. Whenever feasible, pollution that cannot be prevented or recycled should be treated in an environmentally safe manner. Whenever feasible, disposal or other release into the environment should be employed only as a last resort and should be conducted in an environmentally safe manner." Green chemistry aims to design and produce cost-competitive chemical products and processes that attain the highest level of the pollution prevention hierarchy by reducing pollution at its source. For those who are creating and using green chemistry, the hierarchy looks like this. 1. source reduction and prevention of chemical hazards or designing chemical products to be less hazardous to human health and the environment, or making chemical products from feedstocks, reagents, and solvents that are less hazardous to human health and the environment, designing syntheses and other processes with reduced or even no chemical waste, designing syntheses and other processes that use less energy or less water, using feedstocks derived from annually renewable resources or from abundant waste, designing chemical products for reuse or recycling, reusing or recycling chemicals too. Treating chemicals to render them less hazardous before disposal. 3. Disposing of untreated chemicals safely and only if other options are not feasible. Chemicals that are less hazardous to human health and the environment are less toxic to organisms, less damaging to ecosystems, not persistent or bioaccumulative in organisms or the environment, inherently safer to handle and use because they are not flammable or explosive. Thanks for watching my video. Please subscribe to my channel Chem